expressed in terms of reproduction, is decreasing as we go up this arrow. And there were, the points were basically falling right along this line, suggesting that as the costs of immunity are decreasing, hosts can basically invest more, have faster recovery rates, right? But that imposes selection in turn for parasites to increase their virulence. And so it's almost like a decreasing cost of immunity can lead to an escalating arms race in a coevolutionary context. Another really interesting result coming out of this is now to have the strength of immunopathology arising here, arising from the interaction. So for example, if immunopathology causes death only at really high parasite densities and really high rates of immune activation, which does seem to apply to certain of the infectious diseases we like to think about. It was a very interesting coevolutionary result where you actually expect at the highest levels of that kind of immunopathology that hosts and parasites actually have a shared interest in basically tolerating. ESS recovery rate falls to 0 above some threshold, and hosts should just tolerate the pathogen rather than bear that cost of immunopathology. So speaking of tolerance, all of this very much has to do with tolerance, and some work by Lars in the past few years has been extending the use of this term into animal biology, and how it's defined is sort of reduction of the damage done by parasites rather than their numbers per se. And I would argue, and I have done so with Tom last year, that tolerance does does include avoidance of immunopathology. It's not the only mechanism by which parasites might be tolerated by their hosts, but it does include that, and it's likely to be under joint control of host and parasites. So we sort of started into the thinking about the coevolution of virulence in that paper, though not quite as in such detail as I have with Troy. And then finally, the theory that has been done on this suggests that the mechanism again does matter for predicting evolutionary consequences of tolerance. So for example, this paper by Martin Miller showed that whether there's a constant or nonlinear reduction of virulence across a range of parasite densities really matters for the evolutionary outcome. So I think it's early days with all this. We're just starting to dive into the complexity, but I think we're starting to get into the meat of the issues now. Okay, so all these phe's, the coefficients of this linear statistical model, are really seem to be important for the trajectory of evolution that you expect, but are they estimable? You know, I like my theory, but I also like to be able to get into the lab or the field and measure things. So most of my work aimed at this has been on Plasmodium schiebodii. It's a rodent malaria. And it's a pretty good example of an inflammatory balancing act. Basically, protection on the one hand, you need enough inflammation, enough immune activation to kill parasites, but not so much that you kill yourself. These are just a couple of the sort of parasite density time courses, and also this is a mini time course of TNF alpha across several host genotypes. We combine I should say that in order for optimal control of this model infection, definitely need TNF and other pro-inflammatory mediators induced early, but you need to turn them down very quick-like, or all hell breaks loose. So basically, some immunoregulation needs to happen later on. And we've been using some of the immunological toolkit available for lab mice, like monoclonal antibodies and things, to mess with that immune environment. So for example, when we use interleukin-10 receptor blockade, this takes the brakes off the immune system. So this is a density of interferon gamma, another inflammatory cytokine on that y-axis. This is the proportion of red blood cells parasitized. So you read the red points to the left and the black ones to the right. And when we deplete interleukin-10, we take the brakes off the immune system, we see this, this is days post-infection. We see this quite early, quite dramatic increase in the density of those inflammatory markers just freely circulating in the blood. And we do see that this is associated with reduced parasite density. So there's a huge spike in inflammation that is associated with reduced parasite density. So just to put that another way, and now we're looking across 4 different genotypes of that malaria. If we look at total parasite density over time, we find that the IL-10 depleted animals, who are shown in the dark symbols, they tended to have lower peak parasite densities than the control animals who received just an IgG control in the open symbols, but they sure died early. We think we really did shift the proportion of virulence towards immunopathology, away from direct parasite damage and towards immunopathology. Okay, so those are the kinds of time series data we collect. And Grania and I wanted to see the extent to which, using those data, which are actually collected in parallel to the development of the theory, we wanted to see to the extent to which we could actually estimate these parameters. And so we did linear statistical models, basically trying to understand how virulence, so the degree of morbidity experienced by the host, scale with exploitation on the one hand, clearance rate on the other. But because we're actually measuring things in the lab, you can't measure an exploitation strategy, right? And you actually can measure a clearance rate potentially, but there are some complexities there. So it required that we use a few proxies. And I'd be delighted to talk more about those to anyone who's interested, but we sure gave this a go. And we just published this in Evolutionary Applications at the beginning of the year. I just wanted to give you a quick snapshot of the results. We were able, in principle, to make this work, although with the power that we had, the statistical power, we could only estimate 2 of the fees, but they're the ones that scaled with exploitation strategy and with clearance rates. So they're 2 of the important ones we're interested in to understand that evolutionary theory. And I just wanted to focus on the ones here. These are the estimates and the statistical significance of the coefficients for how, in this case, red blood cells are lost per log increase in pro-inflammatory cytokines, and in this case, grams of body mass lost. These coefficients, because they're all significantly different from 0, that immunopathology of the sort that favors tolerance may be very important in shaping malaria evolution. I also wanted to note that we found significant variation in the magnitude of those coefficients among parasite genotypes. That was an additional interesting point when we're interested in the coevolution. So the key parameters do appear estimable, and some of them are even non-zero. But of course, the theory was developed with measles in mind, and measles and malaria ain't the same thing. But we can't even start to consider ramping that up quite yet. Okay, so just to wind down, I want to give a few more caveats. I'm sorry I'm throwing such complexity at you, but I do think it's pretty complicated to get this right. First of all, when we were working with those data, trying to estimate the coefficients, we were using maxima, sort of maximal parasite density as an estimate of exploitation strategy, maximal cytokine density as an estimate of clearance rate. But we all know that maxima aren't everything, right? It's also the time series. You can imagine a really high inflammatory spike that would come down very quickly and, in fact, let the host escape some of the immunopathological costs. So that one challenge is to get some real grip on how to use detailed within-host time series to understand selection pressures on immunopathology. We also had an issue of distinguishing basically how much of the per-parasite damage is purely parasite-mediated and how much is immunopathological. And we think we can get at that using the immunological toolbox, but we haven't quite done it yet. And then finally, in the malaria system, we have this other issue of needing to understand the extent to which immunopathology actually contributes to defense. For any pathogen that is target cell limited, such as malaria is, infecting the red blood cells, in principle, because we know that a lot of the effects, for example, of TNF-alpha are to suppress erythropoiesis. It also causes splenic retention of uninfected as well as infected red blood cells. We have some evidence that Jess Metcalf has been analyzing with us that bystander killing of that sort actually can help protect against malaria. So we may need to actually take a further step back and think about the extent to which self-harm is target cell limitation for parasites, so it may actually be a resistance mechanism in some contexts. So just to summarize, immunopathology causes an awful lot of host damage and death, and it seems to be able to affect trajectories of both parasite and host evolution, but it depends on how the immunopathology arises, the extent to which it's a per-parasite event, it's a random one-off, a parasite gets in the brain, or the extent to which it scales with increasing investment in recovery rate. So those are the main points I would hope you would come away with. But one thing that we really, I think, need to think about this week is the relative role of immunopathology as opposed to just resistance per se, parasite killing mechanisms per se, as an explanation for the heterogeneity and immune responsiveness we see out in nature. I don't know. It might be that immunopathology is only 7% of what the immune system does, right? It might be a pretty important 7%, but it might be pretty minimal compared to what we can learn by studying the evolution of resistance mechanisms. With that, thank you.
Time for a quick question while we phase it up.
So I was wondering with your modeling from Troy, whether you at all played with changing the costs so that maybe from resistance to immunopathology, whether maybe you had reproductive effects on immunopathology or survival effects on resistance, and whether you ever could put it in non-linear, like your models seem to kind of be a linear impact, and I wonder if there's any non-linear.
So we haven't done the reciprocal effects, immunopathology on fecundity or energetic costs on survival. We haven't done any of that. We have messed with non-linear functions, but I can't. The summary from Troy was that it looked pretty good, but I don't remember
You mean
any
as
details.
in
That it looks
very
pretty
different.
robust to non-linear.
And then any kind of putting that any survival effects instead of reproduction, that was the one assumption that I kept thinking might not always be realistic to have
Say again?
the resistance just be affecting reproductive costs as opposed to linear mechanism. Yeah, I'm just wondering how robust it is to putting those costs.
We
on
haven't
survival
tried that.
effect.
We really just started by having immunopathological costs impact survival only, and then sort of energetic or investment costs were affecting reproduction. So we haven't done it at all. I'm working on